Journey through our solar system, rediscovering our cosmic neighborhood. Have you ever gazed up at the night sky and wondered about the mysteries that lie beyond our planet? What powers the blazing heart of our solar system, and how did life-sustaining water come to be on Earth? These are just a few of the tantalizing questions we'll explore together in this documentary. Imagine uncovering the secrets of the sun, the colossal furnace that fuels every moment of life on Earth. We'll delve deep into its core to understand the forces that drive it and how it shapes everything in our solar system. But the sun is just the beginning of our journey. As we venture further, we'll explore the rocky worlds of the inner planets, each one with its own unique story to tell. From the scorched surface of Mercury to the cloud-covered mysteries of Venus and the red deserts of Mars, each planet offers a glimpse into the past and perhaps even the future of our own world. But our exploration doesn't stop there. We'll set our sights on the outer reaches of the solar system, where the majestic gas giants reign. These colossal planets, with their swirling storms and countless moons, are like entire mini-solar systems, each with its own set of wonders waiting to be discovered. We'll navigate through the enigmatic Asteroid Belt, a region filled with ancient remnants from the birth of our solar system, and then journey to the intriguing dwarf planets like Pluto, which challenge our very understanding of what it means to be a planet. As we push further into the dark, icy edges of our solar system, we'll encounter the mysterious Kuiper Belt and the distant Oort Cloud. These regions are home to some of the most distant and least understood objects in our cosmic neighborhood, holding secrets that could rewrite what we know about the origins of our solar system. But this documentary isn't just about facts and figures. It's a voyage of discovery, a chance to see our universe through new eyes and understand the profound connections between these celestial bodies and our own existence. Each segment of our journey will reveal new wonders and deepen your understanding of the universe. From the smallest asteroid to the largest gas giant, from the heat of the sun to the cold depths of space, you'll uncover astonishing truths and witness the awe-inspiring beauty that lies just beyond our reach. We invite you to stay with us until the very end, because the further we go, the more incredible the revelations become. Whether you're a seasoned stargazer or a curious novice, this documentary will leave you with a newfound appreciation for the vast and intricate cosmos we call home. Your voyage of discovery begins now. Fasten your seatbelt because the wonders that await are beyond imagination. The sun, our solar system's heart. Since the dawn of time, the sun has been our guiding light, a fiery orb in the sky that sustains life on Earth and governs our solar system. Join us as we journey into the heart of our star, exploring its structure, its incredible power, and the latest discoveries that continue to awe and inspire. At the heart of the sun lies the core, a cauldron of unimaginable heat and pressure where the fundamental process of nuclear fusion occurs. Here, hydrogen atoms collide and fuse to form helium, releasing energy in the form of light and heat. This core, just a mere 20% of the sun's radius, boasts temperatures soaring to around 15 million degrees Celsius and densities over 150 times that of water. It's a realm of raw power, where every second, 600 million tons of hydrogen are converted into energy, sustaining the sun's luminescence. Surrounding the core is the radiative zone, a vast expanse where energy moves outward in the form of electromagnetic radiation. Photons created in the core can take thousands, even millions of years to traverse this dense, tightly packed region, constantly being absorbed and re-emitted by particles within. This journey is a slow, painstaking trek through a labyrinth of particles. As energy reaches the convective zone, the dynamic changes. Here, cooler plasma sinks while hotter plasma rises, creating a convective current much like a boiling pot of water. This churning motion not only transports energy to the sun's surface, but also generates the powerful magnetic fields responsible for many solar phenomena we observe. Emerging from the depths, we arrive at the photosphere, the sun's visible surface, radiating light and heat that reaches Earth. This thin layer, just 500 kilometers thick, is where sunspots appear, dark patches caused by magnetic disturbances that lower temperatures to about 3,800 degrees Celsius, compared to the surrounding 5,500 degrees. Above the photosphere lies the chromosphere and the corona, the sun's outer atmospheric layers. The chromosphere, a thin, fiery red layer visible during solar eclipses, is a realm of spicules and prominences. But it is the corona that truly fascinates scientists. Despite being less dense, the corona's temperatures soar to several million degrees Celsius, a mystery still being unraveled by astrophysicists. This outermost layer extends millions of kilometers into space, its ethereal glow visible during total solar eclipses. Importance of the Sun. The Sun is far more than a celestial object. It is the cornerstone of life on Earth. It is the ultimate source of energy, driving photosynthesis in plants, which in turn produces oxygen and sustains the food chain. Without the Sun, life as we know it would cease to exist. The Sun's influence extends beyond biology. It dictates the climate and weather patterns, driving the water cycle that sustains rivers, lakes, and oceans. The energy from the Sun warms the Earth's surface, creating winds and ocean currents, shaping our planet's diverse climates and ecosystems. In recent years, humanity has harnessed the Sun's power through solar technology, converting sunlight into electricity. Solar panels, once a novelty, are now a cornerstone of sustainable energy solutions, providing a clean, renewable source of power. As we face the challenges of climate change, the Sun's energy offers a path towards reducing our dependence on fossil fuels and mitigating environmental impact. But the Sun's influence isn't always benign. Solar activity such as solar flares and coronal mass ejections can disrupt communications, navigation systems, and even power grids. Understanding these phenomena is crucial for protecting our technology-dependent society. The study of solar weather helps us prepare for and mitigate the impacts of these powerful solar events. Solar phenomena. Sunspots, those dark patches on the Sun's surface, are far more than blemishes. They are windows into the Sun's magnetic activity, regions where magnetic fields are thousands of times stronger than Earth's. These spots can grow to sizes larger than Earth itself, and often appear in pairs or groups. The study of sunspots has revealed much about the Sun's 11-year solar cycle, a period during which the number of sunspots waxes and wanes, influencing solar radiation and space weather. Solar flares are among the most violent events in our solar system. These sudden eruptions release a torrent of electromagnetic radiation, including X-rays and ultraviolet light, that can reach Earth in minutes. The energy unleashed by a solar flare is equivalent to millions of hydrogen bombs detonating simultaneously. These flares can cause radio blackouts, damage satellites, and pose risks to astronauts in space. Even more dramatic are coronal mass ejections, CMEs, colossal clouds of solar plasma and magnetic fields hurled into space at millions of kilometers per hour. When these CMEs collide with Earth's magnetic field, they can trigger geomagnetic storms, disrupting power grids, communication networks, and navigation systems. They also produce spectacular auroras, lighting up the polar skies with shimmering displays of green, red, and purple. The study of these phenomena is not just an academic exercise. It has practical implications for our technology-driven world. Space weather forecasting aims to predict solar activity and mitigate its effects on Earth, ensuring the safety of satellites, astronauts, and terrestrial technology. Latest discoveries. Humanity's quest to understand the Sun has led to remarkable advancements in space exploration. NASA's Parker Solar Probe, launched in 2018, is on a daring mission to touch the Sun, flying closer to our star than any spacecraft before. It aims to unlock the secrets of the corona's extreme temperatures and the origins of the solar wind, the stream of charged particles flowing from the Sun that influences the entire solar system. The European Space Agency's Solar Orbiter, launched in 2020, complements this mission by capturing high-resolution images of the Sun's poles, regions previously shrouded in mystery. These missions are providing unprecedented insights into the Sun's behavior, from its magnetic fields to the complex dynamics of its atmosphere. Recent discoveries have shed light on the heating mechanisms of the corona, a long-standing enigma. Scientists have observed nanoflares, tiny but frequent bursts of energy that might collectively heat the corona to its scorching temperatures. Understanding these processes is crucial for comprehending how stars function and evolve. Moreover, advances in helioseismology, the study of solar oscillations, have allowed us to probe the Sun's interior like never before. By analyzing the vibrations on the Sun's surface, scientists can infer the conditions within, much like seismologists use earthquakes to study Earth's interior. These breakthroughs are not just about satisfying our curiosity. They have profound implications for space weather prediction, climate science, and our understanding of stellar physics. As we continue to explore the Sun, we not only unravel the mysteries of our closest star, but also gain insights into the workings of the universe itself. As we continue to explore the Sun, we uncover more about its profound influence on our solar system and our lives. The Sun, our celestial beacon, remains a source of wonder and a reminder of the delicate balance that sustains us. From the fiery core to the serene corona, from the sunspots to the solar winds, our star is a dynamic, ever-changing entity that shapes our existence. In its brilliance, we find not only light and warmth, but also the key to understanding the cosmos. Mercury, the swift and mysterious planet. In the vast expanse of our solar system, closest to the Sun, lies a world of extremes and mysteries. Mercury, a planet of stark contrasts and intense heat, Mercury captivates with its unique characteristics and enigmatic nature. It's the smallest planet in our solar system, is a rocky world with a diameter of just 4,880 kilometers. Despite its size, it holds significant geological and physical features that offer a glimpse into the early solar system. At the heart of Mercury lies a massive iron core, making up about 85% of the planet's radius. This core is believed to be partially molten, driving a weak magnetic field, a rarity among terrestrial planets. Surrounding the core is a silicate mantle and a crust that is only about 35 kilometers thick. This thin crust is scarred with impact craters, ridges and basins, remnants of a violent history marked by collisions with comets and asteroids. Mercury's surface is a testament to its turbulent past. The Caloris Basin, one of the largest impact basins in the solar system, stretches over 1,500 kilometers across. This vast, multi-ringed structure reveals the sheer magnitude of impacts Mercury has endured. Interspersed with smooth plains and rugged highlands, Mercury's terrain is a mosaic of ancient history, waiting to be deciphered. The planet's proximity to the Sun subjects it to extreme temperature variations. Daytime temperatures can soar to 430 degrees Celsius, while nighttime temperatures plummet to a frigid -180 degrees Celsius. These extremes have shaped its surface, causing it to expand and contract, leading to the formation of cliffs and escarpments known as lobate scarps. Mercury may seem an inhospitable world, but its study holds profound importance for understanding planetary formation and evolution. As the closest planet to the Sun, Mercury experiences solar forces more intensely than any other planet. This proximity offers a unique laboratory for studying the Sun's influence on planetary environments. The high density provides clues about its composition and formation. The planet's large iron core suggests that it might have formed from a larger body that lost its outer layers due to a colossal impact or solar radiation. By studying it, scientists can gain insights into the processes that shaped not only our solar system, but also planetary systems around other stars. Moreover, Mercury's surface and geological features offer a window into the early solar system's history. The planet's heavily cratered landscape preserves a record of ancient impacts, helping us understand the frequency and magnitude of collisions that shaped the planets. In addition to its scientific value, its extreme conditions challenge our understanding of planetary dynamics. The planet's thin exosphere, composed mostly of oxygen, sodium and hydrogen, is constantly replenished by solar wind and micrometeoroid impacts. Understanding this delicate balance sheds light on atmospheric processes on other celestial bodies, including moons and exoplanets. Mercury is a planet of unique phenomena, shaped by its proximity to the Sun and its rapid orbital speed. It completes an orbit around the Sun in just 88 Earth days, making it the fastest planet in our solar system. This swift journey creates dramatic effects on its environment and rotation. Its orbit is highly eccentric, meaning it varies in distance from the Sun. At its closest approach, or perihelion, Mercury is just 46 million kilometers from the Sun. This elliptical orbit combined with its slow rotation, results in a unique phenomenon. Mercury experiences a day from sunrise to sunrise that lasts 176 Earth days, twice as long as its year. One of the most fascinating features of Mercury is its magnetic field. Despite its small size and slow rotation, Mercury has a magnetic field about 1% the strength of Earth's. This weak but significant magnetic field creates a magnetosphere that interacts with the solar wind, generating intense magnetic storms and dynamic space weather. Mercury's surface is dotted with peculiar features known as hollows. These bright, shallow depressions are scattered across impact craters and suggest ongoing processes of volatile sublimation, where elements like sulfur and potassium vaporize due to solar heating. The discovery of hollows has sparked interest in understanding the volatile components of Mercury's crust and their role in its geological evolution. In recent years, our understanding of Mercury has been revolutionized by space missions and technological advancements. NASA's Messenger mission, which orbited Mercury from 2011 to 2015, provided a treasure trove of data, mapping the planet's surface in unprecedented detail and revealing its geological and compositional diversity. Messenger discovered evidence of water ice in permanently shadowed craters at Mercury's poles. Despite the planet's scorching daytime temperatures, these regions, shielded from the sun's rays, harbor ice deposits, a surprising find that hints at the presence of volatiles delivered by comets or captured from the solar wind. The mission also detected complex organic molecules within these ice deposits, suggesting that the building blocks of life might exist even on the innermost planet. These findings have profound implications for our understanding of the distribution of organic matter in the solar system. In 2018, the European Space Agency and the Japan Aerospace Exploration Agency launched the Bepi-Colombo mission, a joint endeavor to explore Mercury further. This mission, currently en route, will arrive in 2025 and carry 2 orbiters to study Mercury's magnetic field, exosphere, and surface composition. Bepi-Colombo aims to answer many of the questions raised by Messenger, providing new insights into the planet's formation and evolution. Advances in ground-based telescopes and observation techniques have also contributed to our knowledge of Mercury. Scientists are now able to study the planet's surface composition, detect subtle changes in its exosphere, and monitor its interactions with the solar wind from Earth, complementing the data gathered by space missions. Mercury, with its swift orbit and enigmatic nature, continues to captivate and challenge our understanding of planetary science. As we delve deeper into its mysteries, we uncover not just the secrets of the smallest planet, but also gain broader insights into the processes that govern our solar system. From its scorching days to its frigid nights, from its massive iron core to its dynamic magnetic field, Mercury stands as a testament to the diversity and complexity of planetary bodies. Our journey to explore this swift and mysterious planet is far from over, promising new discoveries and deeper understanding of the universe we inhabit. Venus, the second planet from the Sun, is often called Earth's twin due to its similar size and composition. Yet, beneath its dense clouds lies a world vastly different from our own. At the heart of Venus lies a core composed mainly of iron and nickel, similar to Earth's. Surrounding the core is a silicate mantle that extends outward to the crust. However, Venus's crust is much thinner than Earth's, estimated to be about 50 kilometers thick. This thin crust has been shaped by volcanic activity, with over 1,600 major volcanoes or volcanic features dotting the planet's surface. Venus's surface is a mosaic of volcanic plains, vast lava flows, and deformed highlands. The planet's topography is dominated by 2 highland areas, Ishtar Terra and Aphrodite Terra, which are roughly equivalent in size to the continents of Australia and South America, respectively. The highest peak, Maxwell Montes, rises about 11 kilometers above the average surface level, higher than Mount Everest. One of the most striking features of Venus's surface is its extensive network of rift valleys, mountain ranges, and impact craters. The planet's surface appears relatively young, estimated to be between 300 to 500 million years old, suggesting a complete resurfacing event caused by widespread volcanic activity. Despite its similarities to Earth, Venus's surface conditions are incredibly hostile. The atmospheric pressure at the surface is 92 times that of Earth's, equivalent to the pressure found 900 meters underwater. Coupled with surface temperatures that average around 467 degrees Celsius, Venus is a world of intense heat and crushing pressure. Importance of Venus. Venus holds a unique place in our quest to understand planetary evolution and the potential for life in our solar system. As Earth's closest planetary neighbor and twin, Venus provides a comparative case for understanding the divergent paths of planetary development. The study of Venus helps scientists understand the processes that govern planetary atmospheres and climate. Venus's thick atmosphere, composed mainly of carbon dioxide with clouds of sulfuric acid, serves as a natural laboratory for studying the greenhouse effect. The extreme conditions on Venus highlight the potential consequences of runaway greenhouse warming, offering critical insights into climate change on Earth. Its geological activity and volcanic history offer clues about the planet's interior and its thermal evolution. The lack of plate tectonics on Venus, unlike Earth, raises questions about how heat is transported from the interior to the surface and how this affects volcanic resurfacing and planetary dynamics. Moreover, understanding Venus's atmosphere and weather patterns is essential for comparative planetology. The planet's super-rotating atmosphere, with winds reaching speeds of up to 360 kilometers per hour, and its mysterious polar vortices, challenge our understanding of atmospheric dynamics and circulation. This planet also serves as a potential analog for exoplanets orbiting other stars. Many exoplanets discovered in the habitable zones of their stars are similar in size and composition to Venus. Studying Venus helps scientists develop models to understand the climates and potential habitability of these distant worlds. Venus is a planet of extreme and fascinating phenomena, shaped by its unique atmospheric and geological conditions. One of the most notable features of Venus is its dense reflective cloud cover. These clouds, composed primarily of sulfuric acid, reflect about 75% of the sunlight that reaches the planet, giving Venus its bright appearance in our sky. However, this dense cloud cover also traps heat, creating a runaway greenhouse effect that drives the planet's scorching temperatures. Venus's atmosphere is also characterized by its super-rotation, where the upper atmosphere circles the planet in just 4 Earth days, much faster than the planet's 243-day rotation period. This super-rotation creates powerful winds and turbulent weather patterns, particularly at the poles where massive double-lobed vortices have been observed. Surface conditions on Venus are marked by volcanic and tectonic activity. The planet's surface is dotted with shield volcanoes, lava plains, and large volcanic structures known as coronae. These coronae, unique to Venus, are formed by the upwelling of hot material from the mantle, creating circular patterns on the surface. One of the mysteries of Venus is the periodic appearance of transient atmospheric phenomena known as ashen light. This faint glow, observed during the planet's night side, has puzzled astronomers for centuries. Some theories suggest it may be caused by lightning in Venus's atmosphere, while others propose it could be a result of auroras or chemical reactions. The discovery of phosphine gas in the atmosphere of Venus has sparked renewed interest and debate. Phosphine is a potential biosignature, a molecule associated with microbial life on Earth. Its presence in the highly acidic and inhospitable atmosphere of Venus raises intriguing questions about the planet's potential to harbor life or previously unknown chemical processes. Latest discoveries. In recent years, our understanding of Venus has been significantly advanced by space missions and cutting-edge research. The European Space Agency's Venus Express mission, which operated from 2006 to 2014, provided invaluable data on the planet's atmosphere, weather patterns, and surface conditions. One of the key findings from Venus Express was the discovery of ozone in the planet's atmosphere. This ozone layer, while much thinner than Earth's, plays a crucial role in understanding the chemical composition and dynamics of Venus's atmosphere. NASA's Magellan mission, which mapped Venus's surface with radar in the early 1990s, revealed the planet's topography in unprecedented detail. These radar images uncovered evidence of recent volcanic activity, suggesting that Venus may still be geologically active. The Japanese Space Agency's Akatsuki mission, currently orbiting Venus, is studying the planet's atmosphere in detail. Akatsuki has provided stunning images of the planet's cloud structures and has helped scientists understand the mechanisms behind Venus's super-rotation and polar vortices. The discovery of phosphine in Venus's atmosphere by the International Research Team using the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile has reignited interest in the planet. This unexpected finding has led to a surge in proposals for new missions to Venus to investigate the source of phosphine and its implications for life. Future missions to Venus are being planned, including NASA's Veritas and Da Vinci Plus missions, both set to launch in the late 2020s. Veritas aims to map Venus's surface in high resolution, revealing its geological history, while Da Vinci Plus will study the composition of Venus's atmosphere and seek to understand the planet's climatic and geological evolution. These missions, combined with advances in observational technology, promise to unlock new secrets of Venus, providing a deeper understanding of our mysterious twin planet and its place in the solar system. Mars. Beyond the blue sky of Earth, a red planet beckons us with its stark landscapes and tantalizing mysteries. Mars, our neighboring world, has captured the human imagination for centuries. From ancient astronomers to modern scientists, Mars has been a symbol of exploration and the possibility of life beyond Earth. Mars, the fourth planet from the Sun, is a rocky world with a rich geological history. Its rusty red appearance due to iron oxide on its surface has earned it the nickname the Red Planet. Mars's core is thought to be composed of iron, nickel and sulfur. Unlike Earth, the core of Mars is partially liquid, contributing to the planet's weak magnetic field. Surrounding the core is a silicate mantle, which extends outward to the crust. This crust, averaging about 50 kilometers in thickness, is composed of basaltic rock and is heavily cratered, a testament to its ancient and dynamic history. The surface of Mars is a diverse landscape of vast plains, towering volcanoes and deep canyons. Olympus Mons, the largest volcano in the solar system, stands nearly 22 kilometers high, 3 times the height of Mount Everest. Nearby, the Tharsis region hosts a cluster of other massive volcanoes, evidence of Mars's past volcanic activity. One of the most striking features of Mars is the Valles Marineris, a system of canyons stretching over 4,000 kilometers, roughly the length of the continental United States. This colossal canyon system plunges as deep as 7 kilometers, offering a dramatic glimpse into the planet's geological past. Its polar ice caps, composed of water and carbon dioxide ice, wax and wane with the seasons. These caps, along with the planet's widespread signs of past liquid water, suggest that Mars once had a significantly different climate. The presence of ancient river valleys, lake beds and deltas provides compelling evidence that liquid water flowed on Mars's surface billions of years ago. This planet holds a unique place in our quest to understand planetary evolution, climate change, and the potential for life beyond Earth. As a terrestrial planet with a history of liquid water, Mars offers invaluable insights into the conditions that might support life. The study of Mars helps scientists understand the processes that have shaped terrestrial planets, including Earth. By comparing Mars's geology, atmosphere and climate with our own planet, we gain a deeper understanding of planetary dynamics and the factors that influence habitability. Mars's potential for past or present life is one of the most compelling reasons for its exploration. The discovery of ancient river channels, lake beds, and mineral deposits formed in water suggests that Mars had habitable conditions in its distant past. Scientists are eager to find signs of microbial life, which would revolutionize our understanding of life's prevalence in the universe. Moreover, Mars is a prime target for future human exploration. Its proximity to Earth, the presence of water ice, and its day length, similar to Earth's, make it a potential candidate for future colonization. Understanding Mars's environment is crucial for planning human missions and ensuring the safety and sustainability of astronauts. The exploration of Mars also drives technological and scientific advancements. Missions to Mars push the boundaries of space travel, robotics, and remote sensing, leading to innovations that benefit a wide range of fields on Earth. Mars is a planet of fascinating phenomena, shaped by its unique environmental conditions and geological activity. One of the most notable features of Mars is its thin atmosphere, composed mainly of carbon dioxide, with traces of nitrogen and argon. This thin atmosphere, less than 1% the density of Earth's, means that Mars experiences significant temperature fluctuations. Daytime temperatures near the equator can reach 20 degrees Celsius, while nighttime temperatures can plummet to -73 degrees Celsius. Mars's atmosphere also contributes to its dramatic weather patterns. Dust storms, sometimes enveloping the entire planet, are a common occurrence. These storms can last for days or even weeks, reshaping the landscape and affecting solar-powered missions on the surface. The presence of seasonal changes on Mars is another intriguing phenomenon. The planet experiences seasons similar to Earth due to its axial tilt. These seasons cause the polar ice caps to grow and shrink, and they influence atmospheric pressure and temperature. In the winter, carbon dioxide from the atmosphere freezes onto the polar caps, and in the summer, it sublimates back into the atmosphere, creating dynamic climatic cycles. Mars's geological features also reveal a history of volcanic activity. The massive shield volcanoes in the Tharsis region suggest that Mars was once geologically active. Though the planet's volcanic activity has significantly diminished, these ancient volcanoes provide clues about the planet's interior and thermal evolution. One of the most captivating phenomena on Mars is the presence of recurring slope lineae, RSL. These dark streaks appear on the slopes of craters and canyons during warm seasons and fade in cooler seasons. The exact cause of RSL is still under investigation, but they may be related to briny liquid water seeping to the surface, sparking interest in the potential for current microbial life. In recent years, our understanding of Mars has been greatly enhanced by a series of successful missions and cutting-edge research. NASA's Mars Science Laboratory Curiosity has been exploring Gale Crater since 2012, uncovering evidence of ancient habitable environments. Curiosity's findings of clay minerals and complex organic molecules suggest that Mars had conditions suitable for life in its past. NASA's InSight mission, which landed on Mars in 2018, has been studying the planet's interior. Equipped with a seismometer, InSight has detected Marsquakes, providing unprecedented insights into the planet's internal structure and seismic activity. These findings help scientists understand Mars's thermal evolution and geological history. The Mars 2020 mission, with its Perseverance rover, has taken exploration to the next level. Perseverance is tasked with searching for signs of ancient life in Jezero Crater, a former lakebed. The rover is collecting and catching samples for future return to Earth, marking a significant step toward direct analysis of Martian material. The presence of water ice on Mars has been confirmed by various missions, including the Mars Reconnaissance Orbiter, MRO, and the European Space Agency's Mars Express. These discoveries of ice deposits near the surface have profound implications for future human exploration, as water is essential for life support and can be used to produce fuel. In addition to robotic missions, Mars has become a focal point for international collaboration and private sector involvement. The United Arab Emirates' Hope probe, China's Tianwen-1 mission, and SpaceX's ambitious plans for crewed missions to Mars all reflect the growing interest and investment in exploring the Red Planet. The discovery of methane in Mars's atmosphere by the Curiosity rover and Earth-based telescopes has sparked significant interest. Methane could be a potential biosignature, as it is produced by biological processes on Earth. Understanding the source of Martian methane is a key objective for ongoing and future missions. These missions, combined with advances in technology and international collaboration, promise to unlock new secrets of Mars, bringing us closer to answering the profound questions about the planet's history, its potential for life, and its future as a destination for human exploration. Mars, with its rugged landscapes and tantalizing mysteries, continues to captivate our imagination and drive our quest for knowledge. As we delve deeper into its secrets, we uncover not only the history of the Red Planet, but also broader insights into planetary science, climate dynamics, and the potential for life beyond Earth. From its ancient river valleys to its towering volcanoes, Mars stands as a testament to the diverse and complex nature of planetary bodies. Our journey to explore this intriguing world is far from over, promising new discoveries and a deeper appreciation of the wonders of our solar system. The Asteroid Belt, a journey through the cosmic rubble. Between the orbits of Mars and Jupiter lies a vast region teeming with remnants from the early solar system. This is the Asteroid Belt, a celestial graveyard of rocky fragments and cosmic debris. Once thought to be a single planet that never formed, the Asteroid Belt offers invaluable insights into the history and evolution of our solar system. Join us as we journey through this cosmic rubble, exploring the diverse and dynamic world of asteroids, their significance, and the latest discoveries that are reshaping our understanding of this fascinating region. The Asteroid Belt is a vast ring of rocky debris located between the orbits of Mars and Jupiter. It spans a region approximately 150 million kilometers wide, with millions of individual asteroids ranging in size from tiny dust particles to dwarf planets hundreds of kilometers across. The asteroids in this belt are composed primarily of rock and metal, with a small percentage containing ice and organic compounds. These objects are remnants from the early solar system, leftover building blocks that never coalesced into a planet due to the gravitational influence of Jupiter. At the heart of the asteroid belt lies its largest member, Ceres. Ceres is classified as a dwarf planet, measuring about 940 kilometers in diameter. Its surface is a mixture of water ice and hydrated minerals, and it even hosts a thin atmosphere. Ceres' significance extends beyond its size. It provides clues about the presence of water and the potential for habitability within the asteroid belt. Other notable members of the asteroid belt include Vesta, Pallas, and Hygeia. Vesta, the second largest object in the belt, has a differentiated structure similar to that of terrestrial planets, with a crust, mantle, and core. Its surface is marked by large impact craters and deep grooves, evidence of a tumultuous history. Pallas and Hygeia, though smaller than Ceres and Vesta, are significant in their own right. Pallas's highly inclined orbit and Hygeia's water-rich composition add to the diversity and complexity of the asteroid belt. The asteroids are not evenly distributed, but are found in various regions with distinct characteristics. The main belt is divided into inner, middle, and outer regions, each with different types of asteroids. The inner belt is dominated by stony S-type asteroids, while the outer belt contains more carbonaceous C-type asteroids. There are also metal-rich M-type asteroids scattered throughout the belt. The Kirkwood gaps, regions with fewer asteroids, are caused by orbital resonances with Jupiter. These gaps play a crucial role in the dynamic processes within the asteroid belt, influencing the distribution and movement of asteroids over time. The asteroid belt holds a unique place in our quest to understand the history and evolution of the solar system. As a repository of primordial material, the belt offers a glimpse into the conditions and processes that prevailed during the early stages of planetary formation. Studying the asteroids provides critical insights into the composition and diversity of materials that formed the terrestrial planets. The variety of asteroid types, stony, carbonaceous, and metallic, reflects the different regions of the solar nebula from which they originated. By analyzing these asteroids, scientists can reconstruct the thermal and chemical history of the solar system. The asteroid belt also serves as a natural laboratory for understanding the processes of planetary differentiation. Objects like Vesta, with its differentiated structure, provide evidence of early melting and core formation, shedding light on the internal dynamics of protoplanets. Asteroids are also of great interest due to their potential for impacting Earth. Understanding their orbits, compositions, and physical properties is essential for developing strategies to mitigate the threat of hazardous asteroids. Missions like NASA's OSIRIS-REx and Japan's Hayabusa 2, which have returned samples from near-Earth asteroids, are advancing our knowledge and preparedness for potential future impacts. Moreover, the asteroid belt represents a frontier for future space exploration and resource utilization. The abundance of water and metals in asteroids makes them attractive targets for mining operations, which could support sustained human presence in space. Water extracted from asteroids could be used for life support and fuel production, enabling long-duration missions to the Moon, Mars, and beyond. The exploration of the asteroid belt also drives technological and scientific advancements. Missions to asteroids push the boundaries of spacecraft design, navigation, and remote sensing, leading to innovations that benefit a wide range of fields on Earth. One of the most striking phenomena within the asteroid belt is the presence of asteroid families. These families are groups of asteroids that share similar orbital elements and are believed to be fragments from larger parent bodies that were shattered by collisions. The study of asteroid families helps scientists understand the collisional history and evolution of the belt. The Yarkovsky effect, a force caused by the uneven heating of an asteroid's surface, can alter the orbits of small asteroids over long periods. This thermal force causes asteroids to drift in their orbits, leading to changes in their distribution and potential for collisions with planets. Understanding the Yarkovsky effect is crucial for predicting the long-term behavior of asteroids and assessing impact risks. Asteroids can also experience rotational disruption, where the rapid rotation of an asteroid causes it to break apart. This process, driven by the URP effect, Yarkovsky-O'Keefe-Radzievsky-Paddock, leads to the formation of asteroid pairs and binary systems. Observations of these systems provide insights into the internal structure and mechanical properties of asteroids. The asteroid belt is also a site of transient phenomena, such as asteroid collisions and outbursts. Collisions between asteroids can create debris clouds and temporary comet-like activity. Observations of these events offer a glimpse into the processes of fragmentation and the generation of meteoroid streams that can intersect Earth's orbit. One of the most intriguing phenomena is the potential presence of active asteroids. These objects exhibit comet-like activity, such as the ejection of dust and gas, despite being located within the asteroid belt. Active asteroids challenge our understanding of the distinctions between comets and asteroids and suggest the presence of subsurface volatiles that can be released by impacts or thermal processes. The discovery of water and organic molecules on certain asteroids has profound implications for our understanding of the origins of life. Missions like NASA's Dawn, which explored Vesta and Ceres, have provided evidence of hydrated minerals and subsurface ice. These findings suggest that asteroids could have played a role in delivering water and organic materials to the early Earth, contributing to the emergence of life. In recent years, our understanding of the asteroid belt has been greatly enhanced by a series of successful missions and cutting-edge research. NASA's Dawn mission, which orbited Vesta and Ceres, provided unprecedented insights into the geology, composition, and history of these two major bodies. Dawn's findings revealed that Vesta has a differentiated structure with a core, mantle, and crust, while Ceres has a mixed composition of rock and ice with evidence of past cryovolcanic activity. The European Space Agency's Rosetta mission, although primarily focused on Comet 67P/Churyumov-Gerasimenko, provided valuable data on the link between comets and asteroids. Rosetta's close-up observations of the comet's surface and activity helped scientists understand the similarities and differences between these small bodies. The discovery of the interstellar object Oumuamua, which passed through our solar system in 2017, has opened new avenues of research. Although not part of the asteroid belt, Oumuamua's unusual characteristics and hyperbolic trajectory have led scientists to consider the possibility of more interstellar visitors and their potential impacts on the asteroid belt. Missions like NASA's OSIRIS-REx and Japan's Hayabusa 2 have returned samples from near-Earth asteroids Bennu and Ryugu, respectively. These samples contain pristine material from the early solar system, offering a direct window into the building blocks of planets. The analysis of these samples is ongoing, with the potential to reveal new insights into the composition and history of asteroids. The upcoming NASA mission, Lucy, set to launch in 2021, aims to explore the Trojan asteroids, which share Jupiter's orbit. These objects are thought to be remnants of the primordial material that formed the outer planets, providing a unique opportunity to study the diversity of small bodies in the solar system. Advances in telescopic observations and computational modeling have also contributed to our understanding of the asteroid belt. The discovery of new asteroid families, the refinement of orbital models, and the analysis of asteroid light curves are helping scientists unravel the complex history and dynamics of the belt. The search for potentially hazardous asteroids, PHAs, continues to be a priority. The identification and tracking of PHAs are essential for planetary defense. Collaborative efforts between international space agencies and observatories are enhancing our ability to detect and characterize these objects, ensuring timely responses to potential threats. These missions and discoveries combined with advances in technology and international collaboration, promise to unlock new secrets of the asteroid belt, bringing us closer to answering the profound questions about the formation and evolution of our solar system. The asteroid belt, with its diverse and dynamic population of rocky bodies, stands as a testament to the complex processes that shaped our solar system. From its primordial origins to its ongoing evolution, the belt offers a window into the past and a glimpse of the future of planetary science. As we continue to explore and study this cosmic rubble, we uncover not only the history of the asteroid belt, but also broader insights into the nature of our solar system and the potential for life beyond Earth. Join us in celebrating the marvel of the asteroid belt, a region that, despite its chaotic appearance, holds the keys to many of the universe's profound mysteries. As we look to the future, the exploration of the asteroid belt reminds us that even the most unassuming regions of space can provide the most valuable lessons. The giant of our solar system, Jupiter. Looming as the colossal guardian of our solar system, Jupiter stands as a testament to the wonders of the universe. Its immense size and powerful presence have shaped the fate of countless celestial bodies and protected Earth from potential threats. As we embark on a journey to explore this giant, we uncover the secrets of its swirling storms, its majestic moons, and the powerful forces that make Jupiter a cornerstone of our cosmic neighborhood. Jupiter, the largest planet in our solar system, is a gas giant with a diameter of approximately 143,000 kilometers. Its mass is more than twice that of all the other planets combined, and it exerts a gravitational influence that has shaped the architecture of our solar system. The planet's structure is composed of several distinct layers. At its heart lies a dense core, possibly made of rock and metal, though its exact composition remains a mystery. Surrounding this core is a vast layer of metallic hydrogen, where hydrogen atoms are compressed so tightly that they behave like a metal. This layer generates Jupiter's immense magnetic field, one of the strongest in the solar system. Above the metallic hydrogen layer is an envelope of molecular hydrogen and helium. This region transitions into the visible atmosphere, characterized by its striking bands and zones of clouds. The belts, dark bands of cloud, and zones, lighter bands, are created by Jupiter's rapid rotation, which causes intense jet streams to form. Its atmosphere is a turbulent and dynamic environment, composed mainly of hydrogen and helium, with trace amounts of methane, ammonia, water vapor, and other compounds. The upper atmosphere is dominated by clouds of ammonia crystals, which give the planet its distinctive appearance. One of the most iconic features of Jupiter is the Great Red Spot, a massive storm that has raged for at least 400 years. This anticyclonic storm is so large that it could engulf Earth 2 or 3 times over. It is a testament to the powerful atmospheric dynamics that define Jupiter. Jupiter also has a faint ring system, composed of dust particles ejected from its moons by micrometeoroid impacts. These rings are much fainter and more tenuous than the prominent rings of Saturn, but they provide valuable insights into the processes at work in Jupiter's environment. This planet's significance in the solar system extends far beyond its sheer size and mass. As a dominant gravitational force, Jupiter has played a crucial role in shaping the formation and evolution of our cosmic neighborhood. During the early stages of the solar system's formation, Jupiter's massive gravitational influence helped to clear out debris and planetesimals, shaping the orbits of other planets and preventing the formation of additional planetary bodies in the asteroid belt. This influence continues to protect Earth from potential impacts by deflecting comets and asteroids that might otherwise pose a threat. Jupiter's role as a cosmic shield is complemented by its ability to capture and store small bodies. The planet's gravitational pull has captured numerous asteroids, known as Trojan asteroids, which share Jupiter's orbit around the Sun. These objects provide valuable information about the early solar system and the processes that led to planet formation. The study of Jupiter also offers insights into the nature of gas giants, both in our solar system and in exoplanetary systems. Understanding Jupiter's formation, structure, and atmospheric dynamics helps scientists develop models that can be applied to gas giants orbiting other stars. As one of the most accessible and well-studied gas giants, Jupiter serves as a natural laboratory for understanding these distant worlds. Jupiter's magnetosphere, the region of space influenced by its magnetic field, is the largest structure of its kind in the solar system. It extends millions of kilometers into space, protecting the planet and its moons from the solar wind. Studying Jupiter's magnetosphere provides insights into the interactions between planetary magnetic fields and solar radiation, with implications for space weather and the habitability of planets and moons. Moreover, Jupiter's diverse system of moons, particularly the four Galilean moons, Io, Europa, Ganymede, and Callisto, offers a wealth of scientific opportunities. These moons exhibit a wide range of geological and atmospheric phenomena, from volcanic activity on Io to the subsurface oceans of Europa. The exploration of these moons could provide crucial information about the potential for life beyond Earth. Planet's importance extends to its influence on planetary science, space exploration, and our broader understanding of the cosmos. Missions like NASA's Juno, which is currently orbiting Jupiter, are expanding our knowledge of the planet's composition, gravity field, magnetic field, and polar magnetosphere, revealing the complexities of this giant world. One of the most prominent features of Jupiter is its banded appearance, resulting from the planet's rapid rotation and the circulation of atmospheric gases. These bands are divided into belts and zones, with powerful jet streams flowing in opposite directions along their boundaries. This dynamic system creates a constantly changing and turbulent environment, with storms and vortices forming and dissipating over time. The Great Red Spot is perhaps the most famous of Jupiter's atmospheric phenomena. This giant storm has been observed for centuries and is still a subject of intense study. Recent observations from the Juno spacecraft have provided new insights into the storm's structure and dynamics, revealing complex interactions between the atmosphere and the underlying layers of the planet. Jupiter is also home to numerous other storms and vortices, some of which are almost as large as the Great Red Spot. These include white ovals, which are smaller anticyclonic storms, and brown barges, which are elongated dark regions in the planet's belts. The study of these features helps scientists understand the processes driving Jupiter's atmospheric dynamics and weather patterns. The planet's auroras are another remarkable phenomenon. Jupiter's strong magnetic field interacts with the solar wind and particles from its volcanic moon Io, creating spectacular auroral displays at the planet's poles. These auroras are the most powerful in the solar system and provide valuable information about the interactions between the planet's magnetosphere and the solar wind. Jupiter's magnetosphere itself is a phenomenon of immense scale and complexity. The planet's magnetic field is generated by the motion of metallic hydrogen in its interior, creating a magnetosphere that extends millions of kilometers into space. This magnetosphere traps charged particles, creating intense radiation belts that pose challenges for spacecraft and potential future human exploration. The volcanic activity on Jupiter's moon Io is another extraordinary phenomenon. Io is the most volcanically active body in the solar system, with hundreds of active volcanoes spewing sulfur and sulfur dioxide into space. The tidal interactions between Io, Jupiter, and the other Galilean moons generate immense heat, driving this volcanic activity and creating a dynamic and ever-changing surface. The icy moons Europa, Ganymede, and Callisto also exhibit fascinating phenomena. Europa's subsurface ocean, hidden beneath a thick layer of ice, is of particular interest due to its potential for harboring life. Ganymede, the largest moon in the solar system, has its own magnetic field and shows evidence of geological activity. Callisto, heavily cratered and ancient, offers insights into the history of the outer solar system. These diverse and dynamic phenomena make Jupiter a natural laboratory for studying planetary processes, offering insights into the behavior of gas giants, the interactions between moons and their parent planet, and the potential for habitability in the outer solar system. In recent years, our understanding of Jupiter has been revolutionized by a series of successful missions and cutting-edge research. The Juno spacecraft, launched by NASA in 2011, has provided unprecedented close-up observations of Jupiter, revealing new details about its atmosphere, magnetic field, and interior structure. One of the most significant discoveries from the Juno mission is the complexity of Jupiter's atmosphere. Juno's observations have revealed that the planet's weather systems extend far deeper than previously thought, with powerful jet streams and storms reaching deep into the atmosphere. The spacecraft's microwave radiometer has provided detailed maps of the ammonia distribution within the atmosphere, shedding light on the processes driving Jupiter's weather. Juno has also provided new insights into the Great Red Spot, showing that this iconic storm extends much deeper into the atmosphere than expected. The data suggests that the Great Red Spot's roots penetrate hundreds of kilometers below the cloud tops, challenging previous models of the storm's dynamics. The mission has also revealed surprising information about Jupiter's magnetic field. Juno's measurements indicate that the magnetic field is more irregular and variable than previously believed, with regions of intense magnetism and complex structures. These findings suggest that the processes generating Jupiter's magnetic field are more intricate than those of Earth's. In addition to atmospheric and magnetic discoveries, Juno has provided valuable data on Jupiter's interior. The spacecraft's gravity measurements suggest that Jupiter has a diffuse and partially dissolved core, with heavy elements mixed throughout the planet's interior. This challenges traditional models of gas giant formation and has implications for our understanding of planet formation in general. Jupiter's moons have also been the focus of recent discoveries. The Hubble Space Telescope and ground-based observatories have detected plumes of water vapor erupting from Europa's surface, providing further evidence of a subsurface ocean. These plumes offer a tantalizing opportunity to study the composition of Europa's ocean and assess its potential for habitability. Observations of Ganymede have revealed new details about its magnetic field and surface features, while studies of Callisto have provided insights into the Moon's geological history and the processes shaping its surface. Io's volcanic activity continues to be a subject of intense study, with recent observations revealing new active volcanoes and changes in the distribution of volcanic deposits. The upcoming Europa Clipper mission, set to launch in the 2020s, will further advance our understanding of Jupiter's icy moons. This mission aims to conduct detailed reconnaissance of Europa's surface and subsurface, searching for signs of life and assessing the Moon's habitability. These missions and discoveries, combined with advances in technology and international collaboration, promise to unlock new secrets of Jupiter. Saturn. A jewel of the night sky, Saturn, the second largest planet in our solar system, stands as a beacon of beauty and mystery. Saturn, a gas giant, is primarily composed of hydrogen and helium. Unlike rocky planets, Saturn lacks a solid surface. Its atmosphere is a swirling mass of clouds, primarily made up of hydrogen, with traces of helium and other elements. Its atmosphere features dynamic bands of clouds and violent storms. The most prominent feature is the Great White Spot, a massive storm system that appears roughly every 30 Earth years. These storms can be as large as Earth itself, demonstrating Saturn's intense meteorological activity. Deep within Saturn, the pressure and temperature rise dramatically. Scientists believe that beneath its outer layers lies a core composed of rock and ice. Surrounding this core is a layer of metallic hydrogen, which gives Saturn its strong magnetic field. Saturn's rings are its most defining feature, a dazzling array of icy particles ranging in size from micrometers to meters. These rings are thought to be remnants of moons or comets that were shattered by Saturn's gravity. The rings are divided into several main sections, including the A, B, and C rings, with gaps in between such as the Cassini division. Each ring has its own unique characteristics, shaped by the gravitational influence of Saturn's moons. NASA's Cassini spacecraft, which orbited Saturn from 2004 to 2017, provided us with breathtaking close-ups of these rings, revealing intricate details and structures like ringlets and braids. Saturn is orbited by a diverse collection of moons, each with its own unique features. Titan, Saturn's largest moon, is shrouded in a thick atmosphere and is believed to have lakes of liquid methane on its surface. This makes Titan one of the most intriguing worlds in our solar system. Enceladus, another fascinating moon, has been found to have a subsurface ocean beneath its icy crust. The plumes of water vapor ejected from Enceladus's south pole suggest that this ocean might harbor conditions suitable for life. These discoveries have profound implications for the search for extraterrestrial life and deepen our understanding of planetary science. Saturn has been a source of wonder since ancient times. The planet's majestic rings were first observed by Galileo in 1610, although he couldn't fully understand their nature. Today, Saturn serves as a natural laboratory, allowing us to study planetary ring systems, atmospheric dynamics, and the conditions of moons that may offer clues about the early solar system. The Cassini mission revolutionized our knowledge of Saturn, but the journey doesn't end there. New missions and telescopes continue to provide us with fresh insights. For instance, recent studies using Cassini's data have refined our understanding of Saturn's magnetic field and its interactions with the solar wind. Looking ahead, missions like NASA's Dragonfly, set to explore Titan, and proposed missions to study Enceladus's plumes, promise to further unravel the mysteries of this magnificent planet and its moons. As we continue to explore Saturn, we are reminded of the boundless curiosity and ingenuity that drive our quest for knowledge. Saturn, with its stunning rings and enigmatic moons, remains a symbol of the wonders that await us beyond our home planet. Uranus, the ice giant. Far beyond the familiar realm of the inner planets lies a world of mystery and intrigue, a planet so unique that it defies our expectations and challenges our understanding of planetary science. Uranus, the ice giant, stands as a testament to the diversity and wonder of our solar system. It's the seventh planet from the Sun, is an ice giant with a diameter of about 51,000 kilometers, making it the third largest planet in our solar system. Its mass is approximately 14.5 times that of Earth, yet it is the least dense of the giant planets. The structure of Uranus is composed of three main layers: the core, the mantle, and the atmosphere. At the planet's core lies a small, rocky center surrounded by a mantle of water, ammonia, and methane ices. This icy mantle makes up the majority of the planet's mass and is responsible for Uranus's classification as an ice giant, in contrast to the gas giants Jupiter and Saturn. Above the mantle is the atmosphere, which is primarily composed of hydrogen and helium, with a significant amount of methane. It is this methane that gives Uranus its striking blue-green color, as methane absorbs red light and reflects blue light. The upper atmosphere of Uranus is characterized by a series of hazes and clouds. The temperature in the upper layers is incredibly cold, averaging around -224 degrees Celsius, making Uranus the coldest planet in the solar system. The atmosphere is also home to powerful winds that can reach speeds of up to 900 kilometers per hour, driving the planet's weather systems. One of the most intriguing aspects of Uranus is its unusual axial tilt. The planet's axis is tilted by about 98 degrees, meaning that it essentially rolls around the Sun on its side. This extreme tilt results in unique seasonal variations, with each pole experiencing 42 years of continuous sunlight, followed by 42 years of darkness. Uranus also has a faint ring system, composed of dark, narrow rings made up of small particles. These rings are relatively young and likely formed from the remnants of a moon or other celestial body that was disrupted by the planet's gravity. The internal structure and atmospheric dynamics of Uranus present a fascinating contrast to the other giant planets, offering unique insights into the processes that shape ice giants and their place in the broader context of planetary science. As an ice giant, Uranus offers a window into a class of planets that are fundamentally different from the gas giants Jupiter and Saturn. Understanding the composition, structure, and dynamics of Uranus helps scientists develop models of ice giants, both within our solar system and in the growing number of exoplanetary systems discovered around other stars. Planets' extreme axial tilt and resulting seasonal variations provide a natural laboratory for studying the effects of axial orientation on planetary climate and weather patterns. These studies have implications for understanding the climate dynamics of other planets, including Earth. The planet's magnetic field is another area of significant interest. Uranus has an unusually tilted and offset magnetic field, which is likely generated by the motion of conductive fluids in its mantle. This magnetic field creates a complex and dynamic magnetosphere, which interacts with the solar wind and influences the planet's atmospheric processes. Uranus is also surrounded by a system of moons, each with its own unique characteristics. The largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon exhibit a variety of geological features, from ice cliffs and canyons to ancient cratered surfaces. These moons provide valuable information about the processes that have shaped the outer solar system and the potential for geological activity on icy worlds. The study of Uranus and its moons also informs our understanding of planetary formation and migration. The planet's composition and position in the solar system suggest that it formed further out and migrated inward over time. This migration process has implications for the formation and evolution of other planetary systems, offering clues about the dynamics of planet formation and the distribution of planetary types in the galaxy. The exploration of Uranus is not just about uncovering the secrets of a distant planet, but also about expanding our knowledge of the solar system as a whole. By studying Uranus, scientists can piece together the broader story of planetary evolution, the diversity of planetary environments, and the potential for life beyond Earth. As we continue to explore and study Uranus, we open new windows into the history and dynamics of our solar system, revealing the intricate and interconnected processes that have shaped the planets and moons that share our cosmic neighborhood. Uranus is a planet of extremes, where unique phenomena challenge our understanding and spark our curiosity. One of the most notable features of Uranus is its banded appearance, with a series of faint, narrow cloud bands running parallel to the planet's equator. These bands are driven by powerful winds, which can reach speeds of up to 900 kilometers per hour. The wind patterns on Uranus are complex, with both prograde and retrograde flows creating a dynamic and ever-changing atmosphere. The planet's unusual axial tilt results in extreme seasonal variations. During its 84-year orbit around the Sun, each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. These long seasons create unique atmospheric conditions, with temperature gradients and cloud formations that vary significantly over time. The atmospheric temperature on Uranus is one of the coldest in the solar system, with the upper layers reaching a frigid -224 degrees Celsius. Despite these cold temperatures, Uranus is home to powerful storms and vortices. Recent observations have revealed bright cloud features, thought to be methane ice clouds, forming and dissipating in the planet's atmosphere. Uranus also has a faint ring system, composed of dark, narrow rings made up of small particles. These rings are relatively young and likely formed from the remnants of a moon or other celestial body that was disrupted by the planet's gravity. The rings are divided into two main groups: the narrow, dense inner rings and the broader, more diffuse outer rings. The magnetic field of Uranus is another intriguing phenomenon. Unlike the Earth, where the magnetic field is aligned closely with the rotational axis, Uranus's magnetic field is tilted by about 60 degrees from its rotational axis and is offset from the planet's center. This results in a highly irregular and dynamic magnetosphere, which interacts with the solar wind in complex ways. One of the most remarkable phenomena on Uranus is its auroras. Similar to the northern and southern lights on Earth, these auroras are caused by the interaction of the planet's magnetic field with charged particles from the solar wind. However, the auroras on Uranus are much more irregular and variable due to the unusual orientation and structure of its magnetic field. The moons of Uranus also exhibit fascinating phenomena. Miranda, the innermost of the large moons, is particularly noteworthy for its dramatic surface features, including giant ice cliffs, canyons, and regions of chaotic terrain. These features suggest a history of intense geological activity, driven by tidal forces and possible internal heating. Ariel, another of Uranus's moons, shows evidence of resurfacing and tectonic activity, with fault canyons and smooth plains indicating a dynamic past. Titania and Oberon, the two largest moons, have surfaces marked by large impact craters and ancient geological features, providing insights into the history of the outer solar system. The phenomena on Uranus and its moons offer a unique perspective on planetary science, revealing the diverse processes that shape ice giants and their environments. These phenomena challenge our understanding and inspire further exploration and study. Recent years have seen significant advances in our understanding of Uranus, driven by both space missions and ground-based observations. The Voyager 2 spacecraft, which flew by Uranus in 1986, provided the first close-up images and data of the planet and its moons. This mission revealed the complexity of Uranus's atmosphere, the intricacies of its ring system, and the diversity of its moons. The data from Voyager 2 continues to be analyzed, offering new insights and raising new questions about this enigmatic planet. In recent years, advances in telescope technology have allowed for more detailed observations of Uranus from Earth. The Hubble Space Telescope and ground-based observatories have detected changes in the planet's atmosphere, including the formation and evolution of storms and cloud features. These observations have revealed that Uranus's atmosphere is more dynamic than previously thought, with seasonal changes and weather patterns influenced by the planet's extreme axial tilt. One of the most exciting recent discoveries is the detection of bright cloud features and possible convective storms in Uranus's atmosphere. These storms are thought to be driven by upwelling of material from deeper layers, indicating active weather processes. The detection of these storms challenges previous models of Uranus as a relatively inactive planet and suggests that there is much more to learn about its atmospheric dynamics. The study of Uranus's magnetic field has also advanced, with new models and simulations providing insights into the origin and behavior of the planet's unusual magnetosphere. These studies suggest that the magnetic field may be generated by convective motions in the icy mantle rather than the core, offering a new perspective on the generation of planetary magnetic fields. The moons of Uranus have also been the focus of recent research. Observations of Miranda have revealed new details about its geological features, including evidence of past tectonic activity and possible cryovolcanism. Studies of Ariel, Titania, and Oberon have provided insights into their surface compositions and histories, revealing the diverse processes that have shaped these moons. Future missions to Uranus are being planned, with the potential to revolutionize our understanding of the ice giant and its moons. These missions aim to study the planet's atmosphere, magnetic field, rings and moons in greater detail, providing a comprehensive picture of this unique and intriguing world. The exploration of Uranus is still in its early stages, and each new discovery brings us closer to understanding the complexities of this distant planet. As we continue to study Uranus, we unlock new secrets about the formation and evolution of the solar system and the diversity of planetary environments. Neptune, the distant blue giant. Beyond the reach of the sun's warm embrace lies a world of deep blue mystery, a planet that challenges our understanding and captivates our imagination. Neptune, the eighth planet from the sun, stands as a testament to the far reaches of our solar system, where the environment is extreme and the phenomena are unlike anything we've ever seen. Neptune, with a diameter of about 49,500 kilometers, is the fourth largest planet in our solar system. Despite its distance from the Sun, Neptune is a dynamic and complex world with a unique structure that distinguishes it from the other planets. At the heart of Neptune lies a dense core composed of rock and metal, approximately the size of Earth. Surrounding the core is a mantle of water, ammonia, and methane ices, making up the bulk of the planet's mass. This icy mantle is characteristic of the ice giants, setting Neptune apart from the gas giants, Jupiter and Saturn. Encasing the mantle is Neptune's extensive atmosphere, primarily composed of hydrogen and helium, with a notable presence of methane. It is this methane that gives Neptune its vivid blue color, as it absorbs red light and reflects blue light. Neptune's atmosphere is layered, with the uppermost part characterized by thick clouds of methane ice. Below these clouds, the atmosphere transitions into layers of increasing pressure and temperature, eventually blending into the planet's icy mantle. The temperatures in Neptune's upper atmosphere average around -214 degrees Celsius. But as we move deeper, the temperature rises significantly, reaching thousands of degrees near the planet's core. One of the most intriguing aspects of Neptune's structure is its magnetic field, which is tilted by about 47 degrees relative to its rotational axis and is offset from the planet's center. This results in a highly irregular and dynamic magnetosphere that interacts with the solar wind in complex ways. Neptune's ring system, though faint and composed of dark, narrow rings, adds to the planet's unique structure. These rings are likely composed of dust and ice particles, possibly originating from the breakup of a moon or other celestial body. The structure of Neptune, with its dense core, icy mantle, and dynamic atmosphere, presents a fascinating contrast to the other planets in our solar system. This complexity offers valuable insights into the processes that shape ice giants and their role in the broader context of planetary science. Neptune holds a special place in our solar system, not only because of its unique characteristics, but also due to the critical insights it provides into the formation and evolution of planetary systems. As an ice giant, Neptune helps us understand a class of planets that are fundamentally different from the gas giants Jupiter and Saturn. Studying Neptune's composition, structure, and atmospheric dynamics allows scientists to develop models of ice giants, enhancing our knowledge of both our solar system and the exoplanetary systems beyond it. Neptune's dynamic atmosphere and powerful weather systems, driven by internal heat rather than solar energy, offer a natural laboratory for studying atmospheric physics and climate dynamics. The planet's supersonic winds and massive storms provide extreme examples of weather phenomena, challenging our understanding of atmospheric processes. The planet's magnetic field, with its unusual tilt and offset, is another area of significant interest. Understanding the origin and behavior of Neptune's magnetic field can offer clues about the internal structure and dynamics of ice giants, as well as the generation of magnetic fields in other planetary bodies. Neptune's moon system, particularly its largest moon Triton, provides valuable information about the processes that have shaped the outer solar system. Triton, with its retrograde orbit and geologically active surface, is thought to be a captured Kuiper Belt object, offering a glimpse into the population of icy bodies that exist beyond Neptune. The study of Neptune and its moons also informs our understanding of planetary migration and the history of the solar system. Neptune's position and composition suggest that it may have formed closer to the Sun and migrated outward over time, a process that has implications for the formation and evolution of other planetary systems. Neptune's exploration is not just about uncovering the secrets of a distant planet, but also about expanding our knowledge of the solar system as a whole. By studying Neptune, scientists can piece together the broader story of planetary evolution, the diversity of planetary environments, and the potential for life beyond Earth. As we continue to explore and study Neptune, we open new windows into the history and dynamics of our solar system, revealing the intricate and interconnected processes that have shaped the planets and moons that share our cosmic neighborhood. Neptune is a planet of extremes, where unique phenomena challenge our understanding and spark our curiosity. One of the most striking features of Neptune is its dynamic atmosphere, characterized by powerful storms and supersonic winds. The Great Dark Spot, a massive storm system similar to Jupiter's Great Red Spot, is one of the most famous of these storms. Although it has since disappeared, new dark spots continue to appear, showcasing the planet's volatile weather. Neptune's winds are among the fastest in the solar system, reaching speeds of up to 2,100 kilometers per hour. These winds drive the planet's cloud formations and contribute to the formation of massive storm systems, creating a dynamic and ever-changing atmosphere. The planet's axial tilt of 28.3 degrees results in seasonal changes, though these seasons last for over 40 Earth years due to Neptune's long orbital period. These long seasons influence the planet's atmospheric dynamics, with variations in temperature and cloud patterns over time. Neptune's ring system, though faint, consists of dark, narrow rings made up of dust and ice particles. These rings are divided into several distinct arcs, and their origin is still a subject of scientific study. It is believed that the rings may have formed from the remnants of a moon or other celestial body that was disrupted by Neptune's gravity. The magnetic field of Neptune, with its unusual tilt and offset, creates a highly irregular and dynamic magnetosphere. This magnetosphere interacts with the solar wind in complex ways, producing auroras near the planet's magnetic poles. Unlike the auroras on Earth, Neptune's auroras are more irregular and variable, reflecting the unique orientation and structure of its magnetic field. Neptune's largest moon, Triton, is another source of fascinating phenomena. Triton has a retrograde orbit, meaning it orbits Neptune in the opposite direction of the planet's rotation. This unusual orbit suggests that Triton is a captured object, likely originating from the Kuiper Belt. Triton's surface is a mix of ice and rock, with geysers of nitrogen gas erupting from its surface, creating plumes that rise high into the thin atmosphere. These geysers are driven by seasonal heating and provide evidence of active geology on the Moon. The phenomena on Neptune and its moon Triton offer a unique perspective on planetary science, revealing the diverse processes that shape ice giants and their environments. These phenomena challenge our understanding and inspire further exploration and study. In recent years, significant advances have been made in our understanding of Neptune, driven by both space missions and ground-based observations. The Voyager 2 spacecraft, which flew by Neptune in 1989, provided the first close-up images and data of the planet and its moons. This mission revealed the complexity of Neptune's atmosphere, the intricacies of its ring system, and the geological activity on Triton. The data from Voyager 2 continues to be analyzed, offering new insights and raising new questions about this distant giant. Recent advances in telescope technology have allowed for more detailed observations of Neptune from Earth. The Hubble Space Telescope and ground-based observatories have detected changes in the planet's atmosphere, including the appearance and disappearance of storm systems and variations in cloud patterns. These observations have revealed that Neptune's atmosphere is more dynamic than previously thought, with weather patterns influenced by the planet's internal heat. One of the most exciting recent discoveries is the detection of new storm systems on Neptune. These storms, similar in nature to the Great Dark Spot observed by Voyager 2, provide evidence of ongoing atmospheric activity. The formation and evolution of these storms challenge previous models and suggest that Neptune's weather is driven by complex processes that are not yet fully understood. The study of Neptune's magnetic field has also advanced, with new models and simulations providing insights into the origin and behavior of the planet's unusual magnetosphere. These studies suggest that the magnetic field may be generated by convective motions in the icy mantle rather than the core, offering a new perspective on the generation of planetary magnetic fields. The moons of Neptune, particularly Triton, have been the focus of recent research. Observations of Triton have revealed new details about its surface features and geological activity, including the detection of active geysers and evidence of seasonal changes. These findings provide valuable information about the processes that shape icy moons and their potential for hosting life. Future missions to Neptune are being planned, with the potential to revolutionize our understanding of the ice giant and its moons. These missions aim to study the planet's atmosphere, magnetic field, rings and moons in greater detail, providing a comprehensive picture of this unique and intriguing world. Dwarf planets and the Kuiper Belt, the outer frontiers. Beyond the orbit of Neptune lies a region filled with icy bodies, dwarf planets and mysterious objects that make up the Kuiper Belt. This distant frontier of our solar system holds secrets that challenge our understanding of planetary formation and evolution. Join us on a journey to explore the dwarf planets and the Kuiper Belt, the outer frontiers of our cosmic neighborhood. The Kuiper Belt is a vast, donut-shaped region extending from the orbit of Neptune, around 30 astronomical units, AU, from the Sun, to about 55 AU. It is home to thousands of small, icy bodies, remnants from the early solar system, providing a window into the primordial conditions that existed over 4.6 billion years ago. The concept of the Kuiper Belt was first proposed by astronomers Gerard Kuiper and Kenneth Edgeworth in the mid-20th century. However, it wasn't until 1992 that the first Kuiper Belt object, KBO, was discovered, revolutionizing our understanding of the outer solar system. The Kuiper Belt is analogous to the Asteroid Belt, but it is far larger and contains a much greater diversity of objects. These objects, composed mostly of frozen volatiles like methane, ammonia, and water, are remnants from the solar system's formation, offering clues about its early history and evolution. Among the myriad objects in the Kuiper Belt are several dwarf planets, including Pluto, Haumea, Makemake, and Eris. These dwarf planets are among the largest KBOs and provide a unique opportunity to study the characteristics and dynamics of these distant worlds. The study of the Kuiper Belt has revealed that it is not a uniform region. It contains several dynamically distinct populations, including the classical Kuiper Belt, the scattered disk, and the resonant objects. Each of these populations has a unique history and provides different insights into the processes that shape the outer solar system. As we delve deeper into the Kuiper Belt, we uncover new mysteries and challenges, reshaping our understanding of the solar system's frontier. The Kuiper Belt is not just a collection of distant objects, but a dynamic and complex region that holds the keys to the past and future of planetary science. The dwarf planets of the Kuiper Belt are among the most intriguing objects in our solar system. These distant worlds, with their unique characteristics and diverse environments, provide valuable insights into the nature of planetary formation and evolution. Pluto, the most famous of the dwarf planets, was discovered in 1930 by Clyde Tombaugh. Once considered the ninth planet, Pluto was reclassified as a dwarf planet in 2006. This icy world, with a diameter of about 2,377 kilometers, has a complex and varied surface, featuring plains, mountains, and glaciers of nitrogen ice. The New Horizons mission, which flew by Pluto in 2015, revealed stunning details of its surface and atmosphere. The mission provided evidence of geological activity, including possible cryovolcanism and the presence of a subsurface ocean. Pluto's largest moon, Charon, also showed signs of geological processes, including tectonic features and vast canyons. Haumea, discovered in 2004, is another fascinating dwarf planet in the Kuiper Belt. Known for its elongated shape and rapid rotation, Haumea is unique among the dwarf planets. It is also accompanied by two moons, Hihiaka and Namaka, and has a surface covered with crystalline water ice. Makemake, discovered in 2005, is one of the largest known KBOs and a prominent member of the dwarf planet family. It has a diameter of about 1,430 kilometers and a surface covered with methane ice. Recent observations suggest that Makemake may have a tenuous atmosphere that varies with its seasons. Eris, discovered in 2005, is one of the most massive dwarf planets in the Kuiper Belt, even larger than Pluto. With a diameter of about 2,326 kilometers, Eris has a highly reflective surface and is accompanied by a small moon named Dysnomia. The discovery of Eris was a significant factor in the reclassification of Pluto as a dwarf planet. The study of these dwarf planets provides valuable information about the processes that govern the formation and evolution of planetary bodies in the outer solar system. Each of these worlds has a unique story to tell, shaped by their environments and histories. The dwarf planets of the Kuiper Belt are not just distant objects, but key players in the broader narrative of our solar system's history. As we continue to explore these worlds, we gain new insights into the diversity and complexity of planetary systems. The Kuiper Belt holds a special place in our solar system, offering critical insights into the processes that shaped the early solar system and the formation of planetary bodies. As a repository of icy bodies and remnants from the solar system's formation, the Kuiper Belt provides a natural laboratory for studying the primordial conditions that existed over 4.6 billion years ago. The composition and dynamics of KBOs offer clues about the processes that governed the early solar system, including the migration of giant planets and the formation of planetary rings and moons. The Kuiper Belt is also a source of short-period comets, which originate from this distant region and travel towards the inner solar system. The study of these comets provides valuable information about the composition and behavior of icy bodies, as well as the processes that deliver volatiles and organic compounds to the inner planets. The discovery of the Kuiper Belt and its objects has reshaped our understanding of the solar system's architecture. It has revealed that the outer solar system is far more complex and dynamic than previously thought, with a rich diversity of objects and environments. The study of the Kuiper Belt also informs our understanding of planetary systems beyond our own. Observations of exoplanetary systems have revealed that many of them contain similar belts of icy bodies, suggesting that the processes that shaped our solar system are common in the galaxy. The Kuiper Belt is not just a distant region, but a vital part of the solar system that holds the keys to understanding the broader processes that govern planetary formation and evolution. By studying the Kuiper Belt, scientists can piece together the history of the solar system and the factors that have shaped its diverse array of planets and moons. As we continue to explore the Kuiper Belt, we uncover new mysteries and challenges, driving the quest for knowledge and discovery in the farthest reaches of our solar system. In recent years, significant advances have been made in our understanding of the Kuiper Belt and its inhabitants, driven by both space missions and ground-based observations. The New Horizons mission, which flew by Pluto and continued to explore the Kuiper Belt, has provided unprecedented data about these distant worlds. The mission's flyby of the KBO Arrokoth, formerly known as Ultima Thule, in 2019 revealed a contact binary object with a unique shape and surface features. The data from Arrokoth offers new insights into the processes that govern the formation of KBOs and the early solar system. Advances in telescope technology, including the Hubble Space Telescope and ground-based observatories, have enabled the discovery of new KBOs and the study of their characteristics. These observations have revealed a diverse array of objects, including binary systems, contact binaries, and objects with complex rotational dynamics. Recent studies of the Kuiper Belt have also focused on the presence of atmospheres and geological activity on dwarf planets. Observations of Pluto's atmosphere, for example, have revealed seasonal changes and complex interactions between the surface and atmosphere. The detection of potential atmospheres on other dwarf planets like Makemake suggests that these worlds may be more active and dynamic than previously thought. The study of the Kuiper Belt's population dynamics has advanced, with new models and simulations providing insights into the formation and evolution of KBOs. These studies suggest that the Kuiper Belt's current configuration is the result of complex gravitational interactions with the giant planets, including Neptune's migration and the influence of other massive bodies. Future missions to the Kuiper Belt are being planned, with the potential to revolutionize our understanding of this distant region. These missions aim to study KBOs in greater detail, providing a comprehensive picture of their composition, structure, and dynamics. The exploration of the Kuiper Belt is still in its early stages, and each new discovery brings us closer to understanding the complexities of this distant frontier. As we continue to study the Kuiper Belt, we unlock new secrets about the formation and evolution of the solar system and the diversity of planetary environments. The Kuiper Belt and its dwarf planets stand as a testament to the vastness and diversity of our solar system. These distant worlds, with their unique characteristics and mysterious environments, challenge our understanding and inspire us to explore further. The Oort Cloud, the solar system's boundary. Far beyond the familiar planets of our solar system lies a mysterious and distant region, shrouded in darkness and ice. This is the Oort Cloud, a vast spherical shell of icy bodies that marks the outermost boundary of our solar system. Named after the Dutch astronomer Jan Oort, this enigmatic cloud holds the secrets to our solar system's past and the origins of comets. Join us as we journey to the edge of the solar system, exploring the Oort Cloud's structure, significance, and the latest discoveries that are expanding our understanding of this remote and fascinating frontier. The Oort Cloud is an immense and distant region that surrounds our solar system, extending from about 2,000 to 100,000 astronomical units, AU, from the Sun. It is a vast, spherical shell composed of icy bodies and debris, remnants from the early solar system. The Oort Cloud is divided into two regions: the inner Oort Cloud, also known as the Hills Cloud, and the outer Oort Cloud. The inner Oort Cloud is a dense, disc-shaped region extending from about 2,000 to 20,000 AU, while the outer Oort Cloud forms a spherical shell reaching out to 100,000 AU or more. These icy bodies, often called planetesimals, are composed primarily of water, methane, ammonia, and other volatile compounds. They are remnants from the solar nebula, the cloud of gas and dust from which the Sun and planets formed. These objects have been preserved in their primordial state, largely untouched since the formation of the solar system. The total mass of the Oort Cloud is estimated to be several times that of Earth, although the individual bodies within it are relatively small, ranging from a few kilometers to tens of kilometers in diameter. The combined effect of their sheer number and vast distances makes the Oort Cloud an enormous reservoir of comets. The Oort Cloud is thought to have been formed by the gravitational interactions between the giant planets and the primordial planetesimals. As these icy bodies were scattered outward, they were captured by the Sun's gravity, forming the distant and diffuse cloud we observe today. The Oort Cloud is also influenced by the gravitational pull of passing stars and the tidal forces of the Milky Way galaxy, which can perturb the orbits of these icy bodies, sending them into the inner solar system as long-period comets. The Oort Cloud holds a unique place in our quest to understand the history and evolution of the solar system. As the most distant region of our solar system, it offers insights into the early conditions and processes that shaped the formation of planets and other celestial bodies. The study of the Oort Cloud is crucial for understanding the origins and dynamics of comets. Long-period comets, which take more than 200 years to complete an orbit around the Sun, are thought to originate from the Oort Cloud. These comets, such as the famous comet Hale-Bopp, provide valuable information about the composition and structure of the early solar system. Comets from the Oort Cloud are pristine relics, containing primordial material that has remained largely unchanged since the solar system's formation. By analyzing the composition of cometary nuclei and the gases released during their perihelion passages, scientists can gain insights into the chemical and physical conditions of the early solar nebula. The Oort Cloud also plays a significant role in the broader context of planetary science and the study of exoplanetary systems. Understanding the formation and evolution of our own Oort Cloud can help us infer the presence and characteristics of similar distant reservoirs around other stars. These distant regions may be common features of planetary systems, contributing to our understanding of the diversity and complexity of planetary formation in the galaxy. Furthermore, the Oort Cloud has implications for planetary defense. Long-period comets, due to their unpredictable trajectories and high velocities, pose a potential impact threat to Earth. Understanding the dynamics and behavior of these distant objects is essential for assessing and mitigating the risks they may present. The exploration and study of the Oort Cloud also push the boundaries of our technological capabilities. Missions to study comets, such as ESA's Rosetta mission to Comet 67P Churyumov-Gerasimenko and NASA's upcoming Comet Interceptor mission, are designed to provide detailed observations of these distant objects, advancing our understanding of their origins and properties. One of the most significant phenomena associated with the Oort Cloud is the ejection of comets into the inner solar system. When the orbits of these icy bodies are perturbed by passing stars or the tidal forces of the Milky Way, they can be sent on long journeys toward the Sun. These comets, known as long-period comets, provide a unique opportunity to study pristine material from the outer reaches of the solar system. The Oort Cloud is also thought to be the source of interstellar objects, such as the enigmatic Oumuamua, which passed through our solar system in 2017. These interstellar visitors offer tantalizing clues about the conditions and processes in other planetary systems. The discovery of Oumuamua has sparked interest in the possibility of more interstellar objects originating from distant Oort Cloud-like reservoirs around other stars. The gravitational interactions between the Sun, the Oort Cloud, and passing stars create a constantly changing environment. As the solar system orbits the center of the Milky Way, it passes through different regions of the galaxy, encountering varying densities of interstellar gas and stars. These encounters can trigger comet showers, increasing the number of comets entering the inner solar system. One of the most intriguing phenomena is the potential presence of a distant, undiscovered planet in the outer solar system. Some scientists have proposed the existence of a hypothetical planet 9, whose gravitational influence could explain certain orbital anomalies observed in the distribution of objects in the Kuiper Belt and the Oort Cloud. The search for this elusive planet continues, as it could provide valuable insights into the structure and dynamics of the outer solar system. The study of the Oort Cloud also reveals the interactions between icy bodies and the interstellar medium. As comets from the Oort Cloud approach the Sun, they experience sublimation of their volatile compounds, creating spectacular comae and tails. Observing these processes helps scientists understand the physical and chemical properties of cometary nuclei and their evolution as they travel through the solar system. In recent years, our understanding of the Oort Cloud has been greatly enhanced by a series of successful missions and cutting-edge research. While no spacecraft has yet reached the Oort Cloud, Missions like NASA's Voyager 1 and 2 are traveling toward the edge of the heliosphere, providing valuable data on the boundary regions of the solar system. The discovery and study of long-period comets continue to shed light on the nature and origins of the Oort Cloud. Comet Hale-Bopp, which became visible to the naked eye in 1997, provided a wealth of information about the composition and behavior of Oort Cloud comets. Its bright and extended display allowed scientists to analyze its gas and dust emissions, revealing complex organic molecules and water ice. The study of interstellar objects, such as Oumuamua and Comet Borisov, has also provided new insights into the Oort Cloud and its potential connections to other star systems. These objects, with their unusual trajectories and compositions, suggest that material from distant planetary systems can occasionally enter our own solar system, offering a unique perspective on the exchange of material between stars. Advances in telescopic observations and computational modeling have also contributed to our understanding of the Oort Cloud. The discovery of distant trans-Neptunian objects, TNOs, with unusual orbits has provided indirect evidence for the existence and structure of the Oort Cloud. These observations help scientists refine their models of the cloud's formation and evolution. The development of new space missions aimed at exploring comets and other distant objects is on the horizon. NASA's Comet Interceptor mission, set to launch in the coming years, will target an as-yet undiscovered long-period comet or interstellar object, providing detailed observations of its composition and activity. This mission promises to expand our understanding of the Oort Cloud and its role in the solar system. The search for Planet 9, a hypothetical distant planet that could explain certain orbital anomalies in the outer solar system, continues to captivate astronomers. If discovered, this planet would provide significant insights into the structure and dynamics of the Oort Cloud, as well as the processes that shape the outer regions of our solar system. The Oort Cloud, with its vast expanse and enigmatic nature, stands as the boundary of our solar system, a frontier that challenges our understanding and fuels our curiosity. As we continue to explore and study this distant region, we uncover not only the history of the Oort Cloud, but also broader insights into the nature of our solar system and the potential for life beyond Earth. As we conclude our voyage through the vast expanse of our solar system, we find ourselves back on Earth, our blue planet nestled among the stars. We've journeyed from the fiery core of the Sun to the icy edges of the Oort Cloud, discovering the wonders that lie in between. Each planet, moon, and celestial body has revealed its own story, stories that continue to inspire wonder and curiosity. Our journey has taken us across billions of kilometers, yet we have only begun to scratch the surface of what the cosmos has to offer. The beauty and complexity of our solar system remind us that we are part of something far greater than ourselves, a delicate dance of gravity and time that has played out for billions of years. As we gaze upon the night sky, we realize that exploration is not just a quest for knowledge, but a journey of understanding our place in the universe. The discoveries we've made are not just scientific achievements, they are the building blocks of our future. With every new mission, we move closer to answering the age-old questions. Where do we come from? Are we alone? What lies beyond? Space exploration is not merely a pursuit of scientists and astronauts, it is a mission for all of humanity. It is through this exploration that we not only expand our horizons, but also secure the future of our species. The knowledge we gain today will shape the world of tomorrow. So, as we close this chapter of our journey, remember that the story of our solar system is far from over. New missions are already on the horizon, promising to uncover more of the secrets that lie beyond our view. Whether it's the potential colonization of Mars, the search for life on Europa, or the exploration of distant exoplanets, the spirit of discovery will continue to drive us forward. We invite you to keep looking up, to stay curious, and to never stop exploring. The universe is vast and our solar system is just the beginning. The next great discovery could be just around the corner, or light years away. Thank you for joining us on this journey through our solar system. The adventure has only just begun.